So let's talk about the radio itself and what kind of parts. So first we're going to take a look at a very simple radio. So let's just say you have a walkie-talkie. You press a button, you're transmitting. You don't, if you, otherwise you're receiving. So essentially when you press that button, you're switching between a receiver, a low noise amplifier, and a power amplifier. And this may go through a filter, and then there's an antenna. So essentially this switch is determining the flow between a power amplifier here, and it's a very simple form. So this was really a simple front-end module. A little more complex module might be in this Wi-Fi. In this case, you have two bands, 5 gigahertz, 2.5 bands, and you have a switch determining receive, transmit for these two. There's a Bluetooth coming in here, and if we start having some other radios, the switches might be determining a different, whatever the flow is out to the antenna, and you may have filters for the different bands. Okay, so now we have a little bit more complex. Let's take a look at a 4G smartphone. Now all of a sudden that fairly simple flow has just become incredibly complex. And I'm not going to read all of these standards that are in here, but a phone today, when you move around, you don't know if you're in an area that doesn't have long-term evolution or 4G or even 3G. You want that phone to work everywhere. That's one thing. I go back to the mobile. People just want their phones. They also want Bluetooth. They want Wi-Fi. They want, they want their position locator, GPS, right? They want a ton of different kind of radios. There's over 10 or 11 radios in. So that makes all of a sudden very many of these front-end modules, and it's caused a real disintegration in the chip. So as these standards change, and as they rapidly change, people tend to get chipsets or front-end modules for these different sort of standards. Now you would like to integrate more of them together, and that's where silicon comes in. The power of silicon is being able to implement more and more of these functions on a single chip. So especially with all these switches, and that's essentially what we're doing today. We're sweeping up a lot of these. Now here's some of these cellular standards. You can see it was fairly simple, just a few sub-bands, say GSM. Then it's getting more standard, 2G, 3G. Now we're moving into long-term evolution. And these things are just getting more and more complex. So the point is that it's all these radios and standards, it's driving complexity and a lot of disintegration in the phone. That's why there's still so many parts in the phone when you look at it tear down. And we're trying to use silicon and really these large lithographic nodes to address these radio needs and really bring things together. So I'm going to give you an example of that. And let's take a 180 nanometer technology. Now, I think this is a wonderful example of adaptability. So Burlington was the first site for SOI production for processors. It was also the first place that did copper technology. So we had a 180 nanometer technology that we used for processors. So that was running in the fab. We had that. That was an SOI technology. Now we also had a rapidly expanding RF analog and mixed signal business. And at 180, we had high performance and cost derivative silicon germanium in addition to RF CMOS and derivatives in the bulk. So when the switch application came along, we really needed to address certain problems in a product to make a switch a good switch. The first thing is we just had to have low impedance. So it turns out a 180 nanometer transistor is the same sort of gives you the same sort of on resistances in a string of them as you can have in a PHEM. So essentially you can get low on resistance just using the SOI. Also, the capacitance. SOI has oxide here, silicon here. It has partially depleted, so this is silicon region. These are the CMOS gates, if you will. And there's a source and a drain. So essentially, the source to drain capacitance is very low. So it reduced capacitance. And the next thing is that even though CMOS tend to have lower breakdown voltage than all of those 3.5s, by stringing a bunch of them in, if you put a voltage on one end and tap the other end, you could add them up and get a high voltage capability leveraging SOI. Then we took all of our RF technology and really understood how to make an RF switch out of it. So by doing that, we were able to make switches that had low on resistance and low leakage of signals around them, as well as some other characteristics. And I can tell you that this technology has just completely transformed the industry. At one point, PHEMs were just totally entrenched. And today, we're just, we're basically just taking share and getting into a very large percentage, can't really tell you how much, of the handsets in the world, just based on this technology. So let's talk about another application. So we talked about all that data. That data has to be handled somewhere. So it used to be that you would have a fiber running to every cellular station. So you see around town, you see these stations, you see these big rectangular sort of antennas, and those are your cellular protocol antennas, and they're sending out signals. Well, as that data exploded, they can put more towers up, but they were being limited on how to even get information in and out of those because they only had so many fibers. Didn't want to dig more trenches. So essentially what happened is people started using wireless to aggregate and bring different aggregation points up. So this is the spectrum. You can see that the previous one, methodology, really had a fairly low low data rate. But when we start going up into the bands like 70 and 80 gigahertz, these E-band, instead of like 56 megahertz, now you got a 5 gigahertz band. So this is just transforming. So if you look outside, you see these towers, start seeing these round things on, as well as these rectangular ones. And those are all this wireless backhaul. So this thing has just completely transitioned it. And what we found is our silicon germanium technology can completely be a solution for this. So this is a good example of this. So we took silicon germanium. Now, this shows a silicon germanium transistor. Now, we can change the silicon germanium transistor depending on the node. This shows our latest development effort at 90. You can see this is the power gain of the device at 350 and the FT at 22. I can tell you that these kind of frequencies on silicon just weren't even thought of, 20 years ago, 25 years ago. People were publishing 20 gigahertz kind of numbers. So this field has just, we have really managed to take silicon into high performance. So this is wireless backhaul. We changed it a little bit. We found for the power amplifiers that a lot of the signal was being lost in the wire bonds to the chip. So this is just a plot of maximum gain versus the emitter degeneration. And the wire bonds were essentially making the gain of the device very low. So we just used another silicon trick. We just drilled a hole all the way to the backside and shorted a bunch of vias, and that just dropped the inductance down, and then all of a sudden we're just up to the same kind of gain and efficiencies. So this has enabled us to move into high bands, 2.4, 5.8 gigahertz, and it has just, now we're essentially in cellular as well as this. Now, a system is only as good as it's able to be used. So it's not good enough to have technologies. You have these RF technologies. You have to have very high quality compact models and very high quality design kits so that designers can get first time right RF analog mixed signal design. Now people think about first time right digital design. Usually people don't really think about RF analog and mixed signal designs. Now it all goes back to the quality of the models, and of course the methodology you use, and the process design kits, and a flexible methodology that lets you sort of combine digital and RF analog mixed signal together. So this is an example of what we have, which is our design system, and essentially this is our custom integrated circuit design for our RF analog and mixed signal. And what this shows is essentially models feeding into simulators, feeding into this design flow. So let's just start with the models. And this, by the way, is what we're working on here in Bangalore in our compact modeling lab. These models have to be statistical, they have to go across temperature, they have to go across bias, and what we do is we make them fully scalable. So in our design kits, you can take a CMOS transistor, you can make multiple gates, you can make longer, you can change the gate lengths. They're really fully scalable statistical models across temperature and bias. So it's the quality of these. Digital, it's off or it's on. RF analog and mixed signal, what counts is the quality of the model that you now have to trace the entire curve of operation and derivatives. All the derivatives in the model have to be continuous. So this has really differentiated us, and the Bangalore team has done an incredible job at doing this, these compact models. Now, the SKU file means we take all the statistical aspects of the fab. So when you put them in the models and you simulate, you can make sure that you yield in the fab. Then we have the simulator. There is frequency domain for radio designers. And we have essentially transient design, mixed signal, so you can combine these two, fast simulators for digital. And then we have this flow, which is largely a cadence flow in this custom, but it has many point tools that can be from Mentor Graphics and Synopsys and other providers. But essentially, you simulate, you lay out, you verify that the layout and simulation schematics agree. You do parasitic extraction, so you can accurately do RF analog and mixed signal. Then you re-simulate if you need, and then eventually you GDS it out. So we found this is very effective at really almost getting first-time right designs. So these are the kind of products that we have enabled with this kind of methodology, using really larger lithographic nodes. And these products are, you can see some of them, GPS. I mean, I can't really give brands, but we're practically in almost all of the GPSs. We have smartphones, cell phones, and we've really taken a share and gotten in almost all of the cell phones. We have wireless LANs. I think that the interesting thing about the wireless LANs, especially when they were first developing, we were using our silicon germanium technology, and they were almost, all of the initial ones were almost all using the silicon germanium technology. As it migrated to RF CMOS, we migrated with them, and now they've gone to some of the more advanced nodes, but different parts of this are now being implemented in the silicon germanium. So we, as this changed, we adapted and made the technology available for different applications. Automotive, here's this wireless backhaul. Optical, a lot of our technologies are used in your 10, 20, 40, 100 gigabit. So this is the last slide I have, and I think the message here is that, you know, if you have a fab, you're going to build a fab, you don't necessarily have to think that it has to be the most advanced technology. That what's really important is you actually start with this slide. You figure out what it is you want to do. And then you, and then you go back, first maybe trying some simpler technologies, along with, you know, maybe some more advanced, if you're kind of into digital. You can do both. But the important thing is start with products and work your way back. And I think supporting them with application engineering, good design, these are the kind of things that really make these things successful. And I think being a successful fab that produces product, it really has to be end-to-end, and there has to be all of that appreciation from going from the markets, you know, all the way back. But there's a whole suite of things you can do. I thought Gary gave some good examples of products, but a good focus in those things, and taking the product back, would be a very good approach. Thank you.
Thank you, sir.